Hey everybody, let's check out a few more op-amp circuits, and I just want to highlight the versatility of the op-amp to have different practical applications, and I just want to showcase the method that we're using to solve these circuits. Okay, so this particular configuration is called a summing amplifier, and our intention is to have an output that's the sum of all of the inputs. Okay, so let's use the node voltage method. We have an essential node right here. So let's use KCL at that node. So if I have the current going out, say here first, so the voltage here is Vn, over here is Va, so Vn minus Va over Ra. Now let's go over here, the current here, Vn minus Vb over Rb. Now the current here, Vn minus Vc over Rc. And note how we could just keep adding however many inputs we want. And then now let's go the current over here. So Vn minus V out over Rf. And then the current here, In. Okay, for an ideal op-amp, the current here and the current here, they're both 0. So I and IP are both 0, so this is 0. Also, for an ideal op-amp, the voltage here is the same as the voltage here. Vn equals Vp. But notice this pin is tied to the reference, so the voltage here is 0. This is 0, which means Vn is 0. Okay, so let's finish this. So I'm going to move this to the other side of the equation, and then times Rf. So Vo is negative Rf over Ra, Va, Rf over Rb, Vb, Rf over Rc, Vc. Okay, so just for example, let's say you pick all 4 of these resistors to be 1 kilo ohm. Then, right, this is 1, this is 1, this is 1. So then the output would just be negative Va plus Vb plus Vc. Right, so it's summing the inputs, but it's inverted. So it's really an inverting summing amplifier. But then if you choose different values here, you can scale each individual input. Here, right? You can scale based on the choice of Ra, Rb, and Rc with respect to this feedback resistor. Okay, let's check out a different application. So this one is called a difference amplifier. And our intention here is to have an output that's scaled based on the difference between these two inputs. All right, so let's do KCL at this essential node. So let's find the current this way. Vn minus Va over Ra. Now the current this way. Vn minus V out over Rb, and then the current this way, In. Okay, and then for an ideal op-amp, the current here is 0, the current here is 0, so this is 0. And also for an ideal op-amp, the voltage here is the same as the voltage here. Vn equals Vp. Okay, what is the voltage here? Let's just focus on this part right here, and let me draw the current. So the current right here, IP, is 0 for an ideal op-amp. So there's no current here, which means however much current is going here also goes here, which is the same as saying these two resistors are in series. So let me draw it more like this. Okay, so this is our C, this is our D. Right here, here to here, this is VP, and our reference is here. Right, so it's a voltage divider. VP is RD over RC plus RD times this. So VP equals Vn for an ideal op amp. So this goes here and here. So let me write that right now. So I'll rewrite this over here. Vn times 1 over Ra plus 1 over Rb minus Va over Ra minus Vo over Rb equals 0. Vn equals Vp, and Vp is this. So this goes right there. I'll put that right there. Vp is D over Rc plus Rd times Vb. Okay, and then we can take this, move it on the other side of the equation, and then multiply everything by Rb, and there you go. This is the output voltage, which is a function of these two inputs, but let's simplify this. It's still kind of a mess, the algebra. So let's see. Let's clean this up a little bit. If I multiply this term by Rb over Rb, and I multiply this by Ra over Ra, then they have a common denominator. Okay. And then the rest of it, Rb, Rd. Okay. And let's see, this cancels this. So we have Rd over Ra okay. I think we can do a little bit better. Let's simplify a little bit more. Okay, so if you see here, let me multiply this term right here by Rb, and then divide by Rb. And then I'll multiply this term by Rd, and then divide by Rd. Okay, so then what do we have? Ra over Rb plus 1, and then this term right here, Rc over Rd plus 1, okay, and then see this cancels this. Let me just cross that out. Okay, and then let me just write Ra over here. Okay, so let me bring the picture over here so we can look at it. Okay, now do you see Ra over Rb and Rc over Rd? If this ratio between Ra and Rb, if it's the same ratio as Rc and Rd, so if as engineers we design the circuit, so for example, if RB is 10K and RA is 1K, then the ratio is like 1 over 10, like RA over RB. So let's say RA is 1K, RB is 10K. And then we choose to make the ratio here the same. So like, for example, 500 ohms, and this one is 5K. They're the same ratio. If that's true, you see how this whole term becomes 1? So if this is true, we purposely make the ratios the same, then the output just becomes RB over RA times 1 VB minus RB over RA VA. Okay, so then it really is, the output is just the difference of the inputs, and then there's a gain based on what ratio we choose here. Okay, so focus on the method we employed more so than the actual answer. Okay, so if you have any questions, let me know in the forum, and I'll see you on the next video.